Okay, to refresh what we've been doing for the last few days, we've been emphasizing length scales, time scales, mass scales, and finally energy scales. And looking at getting some familiarity with what are optimal units in which to measure these things in, and what is the optimal size of things. How big is a cell? How big is an organelle inside a cell? How big is a bacterium? How much does the bacterium weigh? How much of that weight, of that dry weight, is carbon? How much of water is there inside? How can we estimate these things in a rough and ready way? And even in the latest assignment that I've just given you, that also calls for more types of estimates. One or two of those things I have not taught in class. I think there's some DNA related problem, which is not something that we have discussed so far. But along with the PDF file that I gave you, there was an additional sheet with sort of many of the things that I discussed in class, measures, and ways to estimate various quantities. Use that together with the problem set in order to understand how to answer these questions. So the last thing that we did was energy scales. And remember that we said the energy scales associated with thermal temperature, room temperature, is obtained by saying there is some quantity called Kb, which is 1.38 to 10 to the power minus 23 joules per Kelvin. I think this 23 is correct. And T is whatever temperature you have. For example, T room, you might assume it to be roughly 300 Kelvin. Okay. So multiplying this quantity by the temperature, you get an idea of what is the energy scale associated with a temperature. So energy scale technically associated with random thermal motion. We can use this to estimate various quantities. For example, if you wanted to find out what is the average energy of something in thermal equilibrium, what we would say is that if the average energy is kinetic in character, this is 1/2 times the mass times the average value of V squared. Okay? Half mv squared is the kinetic energy, which you will remember. But now remember that the velocity is not precise and fixed and it's not moving in one straight direction, one straight line with a fixed velocity. It has some average value of the velocity and some average value of v squared. This is a better measure because for something that is not moving in one direction at average, the average value of v is 0. So there are fluctuations about this average value, and it's these fluctuations that should enter the estimate of what is the kinetic energy. To estimate this, we said, okay, let us just equate it to the quantity 3/2 kBt, because this is the amount of energy that you get from thermal fluctuations. And the factor of 3 is in 3 dimensions. So the factor of half kBt for each one of these, for each one of the directions in x, y, and z, so a total of 3/2 kBt. These factors, because they're order 1, are not very important and it cancel from here. So roughly you can get an estimate of v squared average is kBt divided by m, approximately, where I've ignored factors of 3 and so on. For objects that are very heavy, like you and me, where m is measured in kilograms, this fluctuation is very, 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 very small. So it doesn't affect us at all. We will not be able to see the fluctuation that we have in velocity because we are in contact with a thermal bath. On the other hand, for something that is very light and very small, this v squared, the fluctuation can become very large in comparison to the size. So for example, if you were looking at a small particle, I said, took a colloidal particle, could be anything inside a cell that is fluctuating because things are hitting it and flying off. It's in equilibrium with its surroundings. This object can move by a distance that is larger, for example, than its characteristic size. Once it moves over a distance that is larger than the size that itself defines it, that is something that you can begin to see. So for example, if I said, where is the center of this object going, that might be doing some very complicated trajectory that looks like this. This we call random motion, random or Brownian motion. And this is the manifestation of the fact that is this particle or whatever it is, this organelle, is in an environment that is thermal. So it's experiencing thermal noise or random noise or Brownian motion. By thermal noise, I mean this particle is surrounded by lots of other particles, very small that we can't see, molecules. They're hitting at it constantly, and it's as though this sort of it's in a regime where these forces can add up to give you something that looks like a complicated trajectory if you look only at the particle over here, and you cannot see all of the other particles that are hitting it. So we want to try and understand and characterize this particular type of motion. Try to look at it mathematically, develop a model for it, because this is so important to everything that we will actually need to estimate in terms of how cells behave. Remember that the cell is a very thermal environment. Whenever we talk about physical biology, we have to talk about things that are very small. Anything that is small enough is subject to thermal forces and fluctuations, and the cell must develop strategies for dealing with them. Okay? It must, if it has to transport stuff from one point to another, it must perform that transport in the presence of the disordering noise. So whatever mechanism it develops to do this transport must be robust against noise. So one major question about thermal noise itself is how is a cell maintain robustness against noise? And how could it potentially turn noise to its own advantage? Okay. So now, if you remember from the last time, what we did was that we started writing down a simple model for the random walk. In the random walk, we started off thinking, look, this is a general problem of Brownian motion. And Brownian motion, as a simple model for it, we can develop using ideas of a random walk. And in the random walk, we can even simplify by looking at a one-dimensional random walk. And a further simplification is that this random walk happens on a lattice, on a one-dimensional lattice. So the way we started doing this was that we said, here is a line. A lattice means that the particle can hop only between discrete points, all of which are the same distance from each other. So this must be distance A. One dimension because it can only go in this direction. It cannot go into the board or any other thing. Cannot go into this direction or out of the board. So then we said we have, let us say we have a timer. At every time this timer ticks, the particle can hop either to the left or to the right. So if you have a certain time step, tau, this particle, this Brownian walk, this random walker or the Brownian particle hops either to the left or to the right. If it hops to the right in one step, it is now at this point. If it hops to the left, it is now at this point. Okay? Then we said that we can describe sequences of this motion in terms of characters left, right, right, left, right, left, etc., etc., etc. And given a sequence, suppose I give you n of these symbols here, that will tell you exactly where I have gone in a particular well-defined sequence of steps like this. Okay? Then we tried drawing it out. We said at t equal to 0, it would only be at 0. At t equal to tau, it could either be at +1 or -1, but not at 0 and not anywhere else. At time t equal to 2, there's some probability of it coming back here, but also some probability of it moving to location +2, -2 and 0. So as I do this many, many, many times, I can imagine building up some sort of histogram of the probabilities of visiting different points, and that histogram might in principle look like this. This is now discrete. Remember that these are separated by distance a, and the number of steps, it should be a more symmetric histogram, is that what I want to describe. The number of steps roughly defines how big this histogram gets. The more steps, the more spread out it becomes, because the more chance there is of going very far away. This terminal point of the histogram is all steps, which are everything is to the right. So right, 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 all the way up to right. This terminal point would be left, 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 all the way up to left. And anywhere in between is some combination of lefts and rights. Suppose we ask, what is the displacement? So let's now define a quantity called delta. And delta is number of steps to the right minus number of steps to the left. Okay? So now what we want to do is to calculate what is the average value of delta in a walk of n steps. What is the average value of delta squared in a walk of n steps? These are questions that we could ask, but in general we could ask any questions of, given some function of the number of steps to the right and number of steps to the left, how do we calculate the average value? When I use brackets like this, what I always mean is take the object inside here and multiply it by the probability of that happening. So, it is this object here times the probability of that object summed over all values that it can take. That is going to be my notation. So, when I say average value, I mean average over a probability distribution. So, now in order to find the average value of some function of NR and NL, and this is one function and this is another function, what I need to do is to find the probability P of the number of steps to the right and the number of steps to the left in a walk with n steps. That is what I want to try and describe. Okay. So, now notice first of all that if I have some sequence of lefts, rights, left, 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 right, the displacement is the number of steps to the right minus number of steps to the left. Okay. But now there are many possible configurations like this. For example, another configuration that gives you the same displacement would be something like right, left, 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 right. They just differ in detail in how I specify this, but because the number of steps to the right is the same between here and here, and the number of steps to the left is the same between here and here, the quantity delta is the same. Okay. So, now I have to ask, how do I count the number of configurations like this with a fixed number of steps to the right and a fixed number of steps to the left? I need to count that in order to assign it a probability. The way it is easy to calculate that, the probability of having a certain number of steps to the right, let me say NR, and a certain number of steps to the left is just this quantity in a walk of n steps, n factorial by NR factorial times NL factorial times, if there is equal probability of moving to the left, then this is 1/2 to the power NR and this is 1/2 to the power NL. Okay. This is called a binomial distribution. So, let us try and understand each one of these terms and where they come from. Remember that if I have n steps, any sequence of left, right, etc., each of these comes with the same probability 1/2. Okay. So, any sequence of n steps, each of those individual steps has probability 1/2. That means that this particular term here, which is where the probability comes from, is the same for every sequence of n steps. Okay. And that I know because I could also write this, I could also pull this factor out and write this as 1/2 to the power NR plus NL, which is 1/2 to the power N, okay, which then I can pull out onto the left. What is this factor here and where does that come from? Well, that comes from the fact that if I have some sequence, let's say left, right, right, left, right, left, and I ask how many ways are there of writing this sequence that preserves the number of R's and the number of L's. If there are n such objects, there are totally n factorial ways of putting them. I can pick the first one, pick any one at random and put it in the first slot, put any one at random, put it in the second slot, any one at random, put it in the third slot. So, there are total n into n minus 1 into n minus 2 all the way up to 1 to do that. But once I do that, I must also take account of the fact that which sequences R appears is immaterial. For example, I can rub out this R and put it here and really get the same configuration specification. So, permuting these R's between each other does not change anything, permuting the L's between each other does not change anything. So, n factorial by NR factorial by NL factorial really accounts for the fact that all these R's between themselves are indistinguishable, all the L's between themselves are indistinguishable. So, that is where this particular factor comes in, that enters here, and this is where this other factor comes in. Okay. So, now what we need to do is any quantity, for example delta, if we want to average delta, what we must do is sum over all values, in this case of NR and NL, take the probability of having NR and NL at fixed n and multiply it by this quantity, in this particular case delta NR minus NL. Okay. Now, this sum over NR and NL is actually unnecessary, because this is just can be accounted for by just looking at NR itself, because automatically if I tell you what is N and NR, I have told you what is NL, because of this condition that NR plus NL is N. So, all I need to do is to sum between NR equal to 0, no right steps, to NR equal to N, all right steps, n factorial by nr factorial nl factorial times this quantity, which is 1/2 to the power nr, 1/2 to the power n minus nr, which is the same as nl, which I said I can always take out if it's half and put it out here. It's just 1/2 to the power n. Okay, is that clear so far what we're doing? This defines for me a probability. Any average, this probability specifies a certain, given a certain nr and nl, it tells me what a number is. If I sum over all values of nr and nl that I am allowed to, this gives me 1. If I want to average, I put whatever object I want to average inside here. So for example, this is nr minus nl inside here is the average value of delta. Okay, so that's a good start. So now let's look at this quantity nr averaged, okay, which is just sum over nr equal to 0 to n factorial divided by nr factorial n minus nr factorial times nr, the factor of 1/2 to the power n that comes from that term. And I want to know how to calculate that. Okay, I'm going to simplify it. I'm going to change the problem slightly, and not to do that I'm going to write this in a somewhat different form. What I'm going to do is to say that given a quantity p plus q, where p plus q equal to 1, p plus q to the n has an expansion which is identical to this. It's sum over r equal to 0 to n factorial divided by r factorial times n minus r factorial, p to the r, q to the n minus r. This is the binomial expansion. Okay. If I expand p plus q to the power n, each of these terms can be written in this form. It's a sum over n factorial by r factorial n minus r factorial, p to the r, q to the n minus r. Now you should recognize from here that this and this are really the same. If I take p equal to q equal to 1/2, and I just, instead of r here I put nr factorial, these are really the same things. So it's a slightly more general way of writing the expression that I had written. So p and q here, the interpretation is p is then the probability of hopping to the right, and q is the probability of hopping to the left. Instead of taking p equal to q equal to 1/2, we could choose a slightly more general way of writing it. Which one? This one here? Because this quantity that we were calculating is nr. Remember that anything that we want to calculate has the form probability distribution times that quantity. This is the probability distribution here, this expression that I wrote down here, multiplied by this factor, that's the probability distribution, multiplied by this nr, which is this symbol that I have put in there.
You were taking the average for delta, right?
Correct. So we can, so suppose I want to calculate the average, suppose delta is nr minus nl. The average value of delta is the average value of nr minus the average value of nl. It's as though I have put a bracket like this, but if I add any number of quantities and I average over them, that's just the same as the addition of the averages. I've used that and said, let me just calculate this first and then I will calculate this. And that is just my bad notation, everything is the same. Okay, so now I want to do the following. What I'm just going to write this again in that particular form, because whether I call it R or whether I call it NR is immaterial. It's just notation. So let me just write that out first and write P plus Q to the power N is just a sum over NR equal to 0 right up to the capital power N, N factorial by NR factorial, N minus NR factorial, P to the power NR, Q to the power N minus NR. Okay, you agree with that? That's what we had written. All I've done is instead of R, I've gone back to using my NR because I find that more convenient to do. Okay, So now I notice, let me just do the following. Let me write delta by delta p of this object equal to delta by delta p of this object. This both left and right hand sides are functions of a quantity called p. I am now going to take a derivative with respect to p. Is everybody happy with that? Okay. If I do that, what I get on the left hand side is n into p plus q to the power n minus 1. Okay. On the right hand side, what I will get is a sum over nr equal to 0 to capital N, n factorial divided by nr factorial n minus nr factorial. So here is where I get nr p to the power nr minus 1 q to the power n minus nr. You see what I did? I just took a derivative. I take a derivative of this, I pull down nr and I get p to the power nr minus 1. Is that clear?
So you're saying it was trying to say if we change the properties, how does it vary?
No, I'm doing something even simpler. This is true by definition. I don't even have to take p equal to q equal to half. This is always true.
But P and Q are probabilities of mode, right?
That doesn't matter. It's for right now, for them, this is some function of p and q.
Okay.
I'm saying this function of p and q is equal to this other way of writing p and q. If I have a function of p and q, I can take a derivative of that function with respect to p. And similarly, if I take a derivative, because these two things are equal to each other, I can take a derivative here that must be equal to the derivative here. That's all I'm saying. Not a particularly deep point. But notice now that I have done something useful. I have pulled down a factor of nr. So this part are the same. This part is not the same because I have minus 1, whereas I should have had r here, nr here. So the way to solve that is, instead of just taking delta by delta p, I multiply p into delta by delta p of this left hand side equal to p into delta by delta p of this right hand side. So on the left hand side, I have n times p plus q to the power n minus 1. You agree with that? I multiplied by p on the left hand side. On the right hand side, I have n factorial by nr factorial n minus nr p to the power nr q to the power n minus nr. Okay, equal to sum over nr equal to 0 right up to n factorial by nr factorial n minus nr factorial nr p to the power nr q to the power n minus nr. And this object is just the average value of nr by definition. Okay. So now we can say, let me now take p equal to q equal to 1/2. So then I have p plus q equal to 1/2, that is 1 to the power n minus 1. This is n times p, so this is n divided by 2. P plus q is 1/2. I have chosen p plus q to be 1/2. Okay. So then this will be 1, half plus half is 1. 1 to any power is continues to remain 1, no problem. All I have is n into 1/2 outside, so n by 2. Okay. In fact, in general, all I need to do is to take p plus q equal to 1. Then automatically this is satisfied here. And what I have here is n times p. Okay. So nr averaged is n times p in general. If p is 1/2, that is n divided by 2. Okay. Now, in order to look at the NL part, all I need to do is just the same sort of analysis that I did here. So I will just give you the final answer there, because it's easy to check that this must also be true just by symmetry. The average value of NL is n times q. Okay. Therefore, the average value of delta, which is the average value of the number of steps to the right minus the average value of the number of steps to the left. This is just n times p minus q, which is 0 if p equal to q. Okay. Now we could have guessed that without even doing any of this calculation, because in the case where p equal to q, the distribution, the probability distribution that we had was symmetric about 0. It looked like this, and there was as much to the right hand side as there was to the left hand side. So any average value that you calculate of this, so this is nr minus nl here, this quantity would be symmetric, and therefore the average value would be 0. Okay, so there is no net displacement. So over here what is done is plotting a displacement here delta. Here is the probability of having a certain displacement delta. So the average value of delta, because it's symmetric about 0, must be 0. All right. So in a sense, if I have completely symmetric hopping to the front, to the back, to the left and to the right, this quantity delta gives me no real information apart from the fact that the probability distribution of that quantity is symmetric about the 0. What has additional information though, what is interesting to calculate is not delta, but the average value of delta squared, and that's a little more complicated to do. Okay.
So in this case we can say that n by 2, right?
In this case, in this case for both of these it is n by 2, but in general it is np and nq for both of these things. Is this argument clear? So now delta squared is the average value of nr minus nl, which I will write as n minus nr. Just ignore my, sometimes I write capital N, sometimes I write small n, but it's all the same thing. And I take this and I square it. So this is delta squared, and then I put this average around. Remember, this average says take this quantity, multiply by the probability distribution of nl and nr for an n step walk, and then sum over all possibilities. So, it's a very general thing that whenever anything that you want to calculate, some average value of f, suppose I have a probability distribution of f, I multiply by that f for each value that it can take, and I sum over all possible values. The most basic relationship when we talk about probabilities. So now let's write that. So this quantity is average value of nr minus n plus nr, because the minus n goes through. So that is twice nr minus n, the whole square, and then average. This is the average of 4 nr squared minus 4 n nr plus n squared. Okay, it's just doing simple algebra on the board. So let's now calculate each one of these things separately, and we will use the same type of trick that we used earlier. That is to take repeated derivative of an equation like this. So now when we take one derivative, that pulls down one factor of nr. We take two derivatives, that will pull down another factor of nr. But one thing we have to be a little careful about. In order to get one value of nr out, we multiply that by delta p of this. So we have to do again a little slowly, p times delta by delta p into p times delta by delta p of this quantity to the right, which is nr equal to 0 to capital N factorial by nr factorial n minus nr factorial of p to the power nr q to the power n minus nr. If I do this, this gives me the value of nr squared average. Okay, I need to take two derivatives of this quantity on the right hand side. Each of these derivatives will pull down a factor of nr. And then I have to multiply by these factors of p in order to put back the factor that I lose from here. Is that clear? Okay, so now let's just write that out. That is just p delta by delta p of p delta by delta p of p plus q to the power n. Okay, So let's just do the second derivative, p delta by delta p of p times the derivative of this, which is n times p plus q to the power n minus 1. Okay. I've just pulled this p out here, left it there, delta by delta p operating on this is n p plus q to the power n minus 1, which is now I can take the n out because nothing multiplies that. This is n outside, p outside, delta by delta p of p into p plus q to the power n minus 1. Did you see that? I took this n out here, put it there, wrote it as np, took a delta by delta p that's still remaining, wrote it here, and what is inside this is the p left outside, the p plus q to the n minus 1, which I've written there. Now when I take the derivative operates on two functions, the product of two functions, both of which involve p. So then I must write this as n times p times, the first is delta by delta p, this gives me 1, what I have left is p plus q to the power n minus 1. The second term, the p remains there, but this factor change comes down. So n minus 1 times p plus q to the power n minus 2. That's where I close my bracket. Okay? It's just gone from this step where the delta by delta p operates on the product of these two things. Okay. So now here I can, okay, let me just do the next step. But over right here I can say, let me put p plus q equal to 1 automatically, even if it's true, even if p and q are not equal to half, I will work with that. Okay, this becomes 1, this becomes 1. So this becomes n times p times 1 plus n minus 1 times p. Okay. Now each of these terms I can now sort out. So let me just simplify this once more. This becomes n times p plus n squared p squared np minus p minus n p squared. Is that correct? Just check my algebra as I go along. Tell me if I'm making a mistake somewhere. So np plus np times np, which is n squared p squared, minus np times minus np times p, which is np squared. Okay. So now I have to calculate 4 times that object. So 4 into np plus n squared p squared minus n p squared. That's my first term there. The second term is minus 4n nr. So that becomes minus 4 times n. Now this we just calculated, the average of nr. The average of nr was n times p, if you remember. The last term here is just the plus n squared. So I have a plus n squared here. So this is the average value of delta squared. Kiran, are you clear? Huh? So what I did, so this, all of this calculation was to calculate nr squared. The 4 came from this particular term here, delta squared. So nr squared is this term here, we worked out. But delta squared is 4 nr squared minus 4 n nr plus n squared, because this, when I square this becomes 4 nr squared, take the average. The second term is 2 into nr into n, which is this term here, and the last term is n squared.
So this delta square is equivalent to that?
No. This is only, this quantity is only nr squared. So now I am only calculating this particular term. So let me just write one more step here. This is the same as 4 times nr squared averaged minus 4 n average of nr plus n squared. I don't have anything to average there because that's just a number. So now I'm taking each of these terms, I just calculated this. So I'm going to write this as 4 into that quantity that I just calculated. Okay, 4 into np plus np squared, blah blah. The second term is 4 times n times nr, which is np, which I just calculated. The last term is plus n squared. Okay, so now let me set p equal to 1/2, and let us look for simplifications in this answer. So this quantity then becomes 4 times n divided by 2 plus n squared divided by 4 minus n divided by 4. This term here becomes minus 4 n squared divided by 2. Then I get a term which is plus n squared. And I'm just wondering if I have yeah, that's fine. So let me simplify first the n squared terms. 4 into n squared by 4 is n squared. 4 into n squared divided by 2 is minus 2n squared. The n squared here is a term which is plus n squared. Okay. What remains? What remains are these terms here, that is twice n that comes from here minus n that comes from here, 4 into this and 4 into this. This quantity you can see automatically is 0. It cancels. So what I have left here is 2n minus n, which is just n. So now this answer looks extremely simple and nice.
This means that the total, the variance is total steps.
Yes, exactly. And this is a general property of random walks that are not directed. That if I look at the mean square, the variance as we said, of the position, this quantity is just proportional to n. Okay? We should be a little more careful because this quantity has units. We said it made every time step tau, it made a step of size a. So this quantity here, if I interpret this as a distance traveled, that is the number of steps to the right times the distance traveled to the right minus number of steps to the left times the distance traveled to the left, squared and then average, then this answer will just become delta squared equal to n times a squared. And now this has the right dimension. It is a length here, and so this is dimensionless. This has a dimension of length squared. Okay.
By distance traveled to the right, you mean the displacement, right? By distance traveled to the right would mean the displacement.
The number of steps traveled to the right minus number of steps traveled to the left times the distance is the net displacement. Okay. If I just ask what is the number of steps to the right minus number of steps to the left, that would be the way I initially thought of delta. Now I'm just putting a little bit more insight, saying that what I'm interested in is the distance that my random walker is traveling, in which case this delta is, this is just a number, it has no dimension. I must multiply it by something that has the dimension of a size, of a length scale, this quantity a, in order to get something on the left hand side that is the dimension of a length scale.
This distance is, does it keep track of all the positions the random walk has been to, or is it just the distance from the start to where it has ended?
So in this case, we sort of started off at the origin, and then we moved here, and then we said, with respect to this origin here, what are the number of steps to the right or number of steps to the left? And essentially,
Because distance and displacement are two different things, right?
not as far as I'm concerned here, in the sense that once I measure with respect to 0, whether I say what is the distance traveled to the right or the displacement to the right, it doesn't make a difference. Okay.
So this is mean square displacement, delta square.
Yes.
So
So
that
mean.
should be centered around the mean, right? I mean, mean square is
Correct. But here the mean is at 0.
Yeah, so because we're taking equal probabilities,
Of mo-
actually it doesn't matter. in
It
this
doesn't
case.
matter in this case.
When
But in general it does.
yeah, that's what I'm saying. So
Yes.
in general, we do it about the mean.
Yes, exactly. So in general, if you remember, the mean number of steps moved to the right in our average was n times p. And we said this average value is np. And nr minus L, the average value of the displacement was n into p minus q. So if p and q were different from each other, then on average I would sort of move toward the right further and further as I made more and more steps. So my distribution would then move. So then what I should be calculating is the fluctuation with respect to that changing position. Here I have the advantage that my average is always at 0.
You call this fluctuation the mean square displacement.
Yes. So for example, the right way to do it would be to say this is, okay, so displacement minus average value of displacement squared and then averaged. Okay.
X minus mu.
Minus the mean. So this is the mean value. So it's x minus mu squared and then averaged. But here the advantage is that my displacement average is 0. So I'm really only worried about calculating this. But I could repeat all of this without and do it in a similar way. Okay. This is an important result because this is the result that is true for random walks in general. This result here and the result that I've written down here. So it's so general that there are actually several ways of explaining it that also generalize to higher dimensions. So one way to do it is to say that, look, suppose I'm not interested in just one dimension, but I'm going to imagine a 2-dimensional or a 3-dimensional or in general a d-dimensional lattice of points here. And now I say that I can hop to not just to the neighbor to the right or the left, but I can also hop here, I can hop here in one step. So any sequence of steps, let us say, is first step is E1, second step is E2, and then all the way up to En. So I'm sort of assuming that each of this is E1, E2, E3 are unit vectors. Suppose this might be E1, this vector might be E2. These are unit vectors along the x and y, and this is each step. So to be really careful, I will also put quantities that represent a length which I've moved. So this is the net displacement. Say suppose I start here, I make some sequence of steps and wind up here. So this is just the vector sum of all of these vectors. First step, second step, third step, fourth step, etc., etc., etc. Okay? And this is the end-to-end displacement. Of the random walk, the sort of one end of the random walk to the other end. Okay, that is this quantity R. So now, first of all, just notice that the average value of R, so if I took n steps, this must be 0. If I have the same probability of going right or left or up or down, say probability 1/4 of doing any of these, for every walk that gets me here, there is another mirror image walk where instead of taking E1, I take minus E1, minus E2, minus E3, minus En. So instead of which I land up here. So for any walk, there is a precise walk in the opposite direction, which just corresponds to taking the inverses of all of these. Instead of taking E1, I go minus E1. If you're taking E2, I go minus E2. So for every sequence here of E1, E2, E3, E4, for each of these steps, I just substitute by the sequence that goes in the opposite direction. So then just by symmetry, the same sort of argument that said in one dimension when I hop, on average I'm going nowhere because I have no net bias to go to the right or the left. Even here in 2 dimensions or 3 dimensions, provided the probabilities of going x or minus x, y or minus y, etc. are the same, on average this quantity is 0.
If the distributions are uniform.
If the probability of hopping in any of these directions is the same. So the probability distribution of an elementary step is uniform. across each direction. Uniform means a slightly different one. Uniform means that it's in a continuum thing, but here it means the probability of hopping in any of these 4 directions, d directions in general, is the same. So now let us look at the quantity r squared average as a function of n. So this would be the average of r dot r for an n step. R is the displacement from this point, from any starting point to the end state point. So r is first step. So if I had one step, I moved here, then r would be this vector here. If I made 2 steps and I moved from here to here, r would be a vector in this direction. So after n steps, this is some step that started here and moved here in n steps. But I could have different, depending upon what were the steps I took, I could wind up here or here or here or here or here or here. So this is an average value. And all I'm saying is by symmetry, r and minus r have the same probability. So when I average, those quantities should go to 0. But now I'm interested in calculating the r squared. And the way I do this is, I will write this as, pull the factor of a squared outside, and then I will write this as E1 dot E1 plus E1 dot E2 plus average here plus E1 dot E3 plus average of EK dot EL in general here plus etc 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 etc. So suppose I have n terms here, n into n is the total number of, n squared is the number of terms that I would have to write out here. Okay, that's correct, no? So now over here, notice that there are 2 types of quantities. One is E1 dot E1, E2 dot E2, etc. etc. Averages here. All these quantities must be 1. Okay, there's no way of avoiding that average. On the other hand, if I look at EI dot EJ, where I and j are not equal, that's the correlation between a vector in this direction and some other vector. Both of the nth step of one walk and the nth step of the other walk are not correlated with each other. They could be in opposite direction. So on average, this quantity is 0. Most of the terms in this sum are of this form. There are only n terms which are E1 dot E1, E2 dot E2, E3 dot E3, E4 dot E4. So this answer here for, let us say, r squared average is just a squared into number of steps. This is the same result as the one here. But it's just a little more physically argued as to why this should be the case. Is that clear? Why that should be the case? Equal to 0 for I not equal to j. So again here, within thinking about in general random walks on lattices in more than one, in one dimension we could do it easily using this calculation. In 2 dimensions, 3 dimensions, 4 dimensions it would be a more involved calculation, but the physical argument will tell you that this answer has to remain the same. Okay. So now let us be a little more mathematical about what we want to try and do, and try and write down an equation for the probability. Remember that here we are just calculating r squared. In general we could go to r to the power n. But all of these quantities essentially come from a quantity which is probability distribution of the end-to-end distance r if I make n steps. So what we've calculated now is really saying, look at all possible values of r where you can go in n steps, multiply by the probability distribution of Rn, and multiply this by whatever you want to average. For example, if I wanted to average r here, I would take r and put it there. But this is a more basic and fundamental quantity, because if I know P of Rn, the probability distribution of being, so let me just write it in a sec, probability distribution of being at location r in n steps. If I know this quantity, then I can calculate r average, r square average, r cubed average, r 4e average, anything that I want to calculate in terms of properties of r, I can calculate given the full probability distribution of r for an n step walk. So now,
So probability distribution is the probability density function, right?
is the probability density function, exactly.
So here R is continuing your discussion.
So in all of these examples it has been discrete, but now I want to go to a continuum. So the n steps I will also have to change to something that is changing in continuous time. So remember that when I set up the original problem, we said that I'm making a step every tau times. So if I take a total time t divided by tau is like the number of steps that I have made. So I want to try and see how to take the continuum limit in this to come up with a description of this problem. First of all, we are going to start by imagining some lattice, in general in some d dimension, whether d equal to 1 or 2 and so on. And I am going to define a basic quantity which is called the probability of being at location x at time t if I started at location 0 at time 0. This is going to be now my most basic quantity that I want to try and calculate. So this is location given a vector value x, this is time t greater than or equal to 0, this is starting location, and this is time t equal to 0. So that's a simple question. I start here at a particular point, it need not be 0, could be in general some x prime or x0 or something like that. But I have to tell you where I am starting, I have to tell you when I am starting, and I have to tell you how much further to look in time. What is the later time that you want this answer for? And so now notice that the probability, so yeah, first of all I'm going to hop on a lattice in which this distance is a, and I'm going to hop with a time step whose value is tau. And I want to take tau and a to be very small so that I can simulate being in the continuum. So finally I want to take tau and a going to 0 in a specific way, so that all of this mathematical description makes sense. So the probability of being at location x at time t plus tau, given that I started at location 0 at time t equal to 0, is this particular, I will just write it down and then I will explain it. So this is probability of being at x minus a times, let's say, x hat at time t minus tau given 0 comma 0, plus probability of being at x plus a x hat at time t minus tau given 0 comma 0, plus probability of being at x plus a times y hat at time t minus tau given 0 comma 0, plus the probability of being at x minus a times y hat, blah 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 blah. So what am I doing here? All I am saying is that if I had to be here at time t, then I must have been in one of the neighboring sites at time t minus tau. Because the only way I can get here at time t is to have come either from here or from here or from here or from here. In 2 dimensions, the way that I have drawn it, there are 4 sites from which I could have come. In general, in d dimensions, there are 2d sites from which I should have come. And the probability of each of this, whether I come from here or here or here or here, is the same.
D is what?
D is a dimension. So in D, D equal to 2, 2D equal to 4. I could have come from 4 of these sites. In 3D, 2D equal to 6. I could have come from any 6. So these 4 plus the one outside plus the one inside the board. So that's why this factor of 1 over, this is the probability of hopping from any one of these sites. So this multiplied by the probability of being x minus a hat, this site here. If I was in this site, I could have dropped here. So at time t minus tau, I must have been at this site. So over here at time t minus tau, I must have been at this site, x plus a of x hat. Similarly for the y or for the z and any other term that I might want to, depending upon how complicated it actually is. Okay, you get that? I'm now going to subtract the same quantity from the left and the right hand side. So I'm going to write this at p of x comma t. Sorry, I made a mistake. If this is t plus tau, this must be t, must be t, must be t, must be t. because from t I can go to time t plus tau. This is a minor change there. So what I want to do is I want on the left hand side I'm going to subtract the value at t, so p of x at t plus tau.
So I have done
One sec, I'll just write this. Yeah.
t plus tau.
Hmm.
Y is t. Done.
Because this is the previous time. So the time is counted from 0, say, let us say now I'm at time t, next time is t plus tau, time after that is t plus 2 tau. So the previous, if I'm to be at this particular site at time t plus tau, at time t I should have been in one of these other sites. That's all I'm saying. Okay. So now I'm subtracting this quantity from the left hand side. I should also subtract it from the right hand side. So the way I will do that is, I will put it into the bracket, but then I must multiply by a factor of 2d, because the 2d is sitting outside. Okay? So this is 1 by 2d times the same thing here, p of x minus a hat at time t. I'm going to drop the 0, 0 because I'm always going to assume that I start at 0, 0, plus p of x plus ax hat plus a x hat at t plus blah 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 minus minus 2d times p of x comma t given 0 comma 0. That clear? Because of the 1 by 2d here. So now let's just remind ourselves a little bit about derivatives. For example, p of x plus a minus p of x divided by a. If I take the limit a becoming very small, this is a way of thinking about the derivative p prime of x. This is the discrete way of defining the derivative. Similarly, if I look at p double prime of x, this is p of x plus a plus p of x minus a minus twice p of x divided by a squared. And for that, we'll have to go back and look at the definitions of these derivatives and see why the second derivative is defined in this way. So this is dpx by dx squared, or d2px by dx squared. This is dpx by dx.
So there is no limit.
There should be a limit. So this is a limit in which a goes to 0. Okay. So first of all, this quantity on the left hand side that involves tau, I can write that as p of x plus tau, p of x comma t plus tau given 0, 0 minus p of x comma t at 0, 0. That is this quantity that I had on the left hand side. I'm going to multiply and divide by tau. So multiply by tau, divide by tau here. And then take this tau inside here and then write p of x comma t plus tau given 0 comma 0 minus p of x comma t given 0 comma 0 divided by tau, limit tau becoming very small. This is actually it's delta p of x comma t by delta t. Okay. So keep track of the fact that I have multiplied and divided.
What about the numerator tau?
So just keep track of it, the fact that I have multiplied. We'll sort all those factors out now. On the right hand side, I multiply and divide by a factor of a squared. And now I combine each of these terms, p of x plus a, p of x minus a, minus twice px. And you see there's always enough terms in this to be able to make use of this particular formula for dpx by d, for d2px by dx. Okay? So once I take this, write it in this form, take the a squared inside, then this sort of simplifies, and it looks as though I can write it in that particular derivative, partial derivative form. So let me write it out, and then we can go back to what we wrote and see whether it all makes sense finally. So we had an extra tau sitting here. So tau times delta p x comma t by delta t equal to a squared times delta p, a squared times a whole bunch of terms, which is delta squared by delta x squared times p plus delta squared by delta y squared times p plus delta squared by delta y squared, delta z squared, etc., etc. So if I just have 3 dimensions, I have a term that looks like this. Okay? This is often written in the form a squared times del squared of p of x comma t given 0, 0. That's exactly the definition. Okay? So now let's sort out various terms. Let us now simplify this by writing delta p of x comma t by delta t equal to a squared divided by tau, and I have missed a factor of 2d here. So 2d tau.
Yeah, what happens to the d that is inside? Because
So each of those terms, taken 2 by 2, they do the x-axis, y-axis, z-axis.
yeah, but what happens to the d?
That d is just a number, no? Suppose that in 3 dimensions, this becomes 3 into 2 is 6. So 6 times p of x comma t given 0, 0.
Yeah,
So-
but we need only 2 times px.
Hmm?
Because minus 2px, right?
Now I have a whole number of, so x minus a, x plus a. With this I added 2 times p of xt. Then I have x minus a y hat t, x plus a y hat of t. I take another 2 from here. Third time I have x plus z hat, a times z hat t plus x minus a times z hat t. I take another 2 from here. So there's always enough terms here to be able to compensate these to write this second order expression here. When I do that, I finally write everything in this form. So then I get del squared of p of x comma t. I'm just dropping the 0 comma 0. The only thing I need to be a little more careful about is the definition of p itself. We've not changed that a little bit, because initially we started off saying that the probability of it being here or here or here, it was still defined on that lattice. So what we must do is go from probabilities to probability densities, or probabilities per unit volume. And the way we do that is we sort of, once we imagine that our lattice is going to be very closely spaced, etc., around each one of these points I can make a tiny little volume of size a on side, or a to the d is the actual volume. So if I take p everywhere and I write small p as capital P divided by a to the d, this then becomes my probability density. I can do that on both sides because p appears linearly on both sides.
What's capital P?
Capital P is what we've been working with so far. That's the probability of finding it here or here or here. That's a probability, that's a number. But what I want to do when I want to write things in the continuum is to find a probability density. And this is a general point. Remember that if I have things that are continuously distributed, it makes no sense to say what is the probability of it being exactly here. Because then you have to specify this particular point exactly to infinite number of decimal places. So what you say is what is the probability of finding it in a little interval between here and here, and that question is well defined. In order to do that, I must take probabilities and make them probability densities. So a probability p of x is a probability density p of x times a little interval dx. That's how I define it. So this quantity is a probability per unit length, more generally a probability per unit volume. And the consistent ways to use the same a to define that particular probability. So once I do that, I now have my final step, which is delta p of x comma t divided by delta t is some d times del squared of p, and I have removed all that dependence on 0 and just written it in this form. So now my d is A squared divided by twice dimension d times tau. I just call it d from now on. This is a very famous equation. It's called a diffusion equation. Sometimes it's also called a heat equation, but the diffusion equation is what we will do here. The quantity d is called a diffusion constant. The dimension of d is length squared divided by time. So if I ask what are the dimensions of the diffusion constant d, this is the quantity with the units of dimension length square on top divided by a unit of time L squared. So the correct unit is, for example, micron squared per second or meter squared per second or kilometer squared per hour, whichever way you want to do it. But you have to remember that this is the right unit to use when you discuss the diffusion constant. So this now is an interesting object. So what I am saying is now the probability, I have been looking for a probability distribution in which to understand all the behavior of my random walk. So now the statement is that this particular equation, the diffusion equation, is what will give me all of those properties. So once I study this equation and its properties, I should be able to ask all those questions. What is r squared? What is the average value of r, etc., 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 based on this alone. I should be a little more careful and say the argument here are vector arguments. I drop the x here, but so I just use this here. The probability of, so this quantity here is an equation for the probability density of finding a particle or a Brownian particle within some small volume, infinitesimal volume, about a point x at time t. What is implicit here is the initial condition, because remember, actually speaking, this p of x comma t given 0 comma 0 carries the information of where it started out from. So I can either put that in as an initial condition on this equation, or I can remember where it came from by putting this given 0 comma 0 somewhere explicitly in that, in which case it's encoded into the way I describe the quantity that enters that equation. Okay. So the next time we should start discussing a little bit about the different forms and the usefulness of this equation, what we can calculate from it and what we can do with it. So this was right now just devoted to giving you the continuum description of the same random walk problem that we discussed earlier. Okay. Any questions?
So t is a time step which we finally they make it continuous, like taking small intervals and going.
That's right. That's right. So in the way we did it earlier, if I have a total time t, if I divide it by the time step tau, this gives me the number of steps. So I'm going to imagine that tau going to 0 is really tau going to 0 in such a way as to keep this number of time steps infinite, because I want to parameterize this as a smooth curve. So I have many steps. So the same sort of, I mean, you have to be, technically speaking, you should do this a little more rigorously than I have done it, but this is all I really need it for at this point. And we will show how you can interpret this in other ways. When you think about probabilities, distributions of conserved quantities, that there are simpler, more physical interpretations of these things. But it's important in a physical biology course, because diffusion is so fundamental and basic as a biological phenomenon, that it's important to understand how we model it and what we can do with those models. Anand, you had a question?
I have a confusion regarding the derivation of the tau part.
Which one? This one?
When you multiply tau by tau with this part, right?
I multiply this on both sides.
Okay,
I don't need to multiply it on both sides because I'm just multiplying by 1. If I multiply and divide by tau, I can do that on either side.
okay, no, I am lost by in between, that's why.
Okay, so if we can trace it through, we can work it out right now.
At that point, I got the limit tau tends to 0.
So this one here.
Yeah.
Okay.
At that stage, we just first multiplied by.
So first we wrote down an expression for this quantity in terms of things on the right hand side. It is the probability of hopping from one of the neighboring sides. Then on both on the left and the right hand side, we subtracted this quantity. So then on the left hand side, I have this minus this. Now I multiply and divide by tau. I take the tau inside here. And then I notice that if I take my tau very small, then this minus this divided by tau looks like the expression for the derivative, the finite difference version of the derivative. So now I have this derivative expression, but I also have a tau sitting outside there. So it's tau times delta p by delta t equal to things on the right hand side. Then we simplified the right hand side and wrote this in terms of a derivative here. And I multiplied and divided by a squared, so I still had an a square above here. So now when I take the tau and bring it down, I bring it down here, I have the a squared from the term I multiplied on the right hand side, a tau that came from the left hand side when I brought this down, and a factor of 2d from my original definition. So this whole quantity here I will now call a diffusion constant and simplify this equation to this particular form. Okay? This is now a probability density. Because I have been careful about taking x going to 0, tau going to 0, etc. But I left this p the same. But when I go to the continuum limit, I must go to a continuum distribution of all quantities here. So now p is no longer the p that it was initially, it has to become probability density. But it's easy to do that because all I need to do is to divide by the same a to the d, the small little volume here, and just remember how I define this. A probability density from the probability. This is the same as saying the probability density is a probability divided by this little dx.
What does this equation tell us?
This equation is now an equation for the probability density. Given an initial probability density p of 0, 0, this tells you how it changes. So a simple physical way of describing it is that suppose I have my random walker who is diffusing. At time, so suppose this is the position in one dimension x, this is my origin, and I am looking at what happens at time. So at time t equal to 0, it's precisely here, it's nowhere else. As I go in time, a little later in time, it could have gone a little distance. Somewhat later, even more later in time, it could go like that. Even more later in time, it does this. If I wait infinite amount of time, it basically is uniform. So these probability distributions of the random walkers are not like the normal probability distribution that you have studied earlier, which are independent of time. It depends upon how much time there is elapsed since the initial condition. So those probability distributions, but given any one of these, suppose this is the time t equal to 10, I can calculate the properties of the random walker at that time without a problem, provided I know what is the right probability distribution at that time. So what this equation gives you is a way of understanding or describing the probability distribution at different times and how it changes. That's right. So the distribution is changing in time, and if I solve this, I can tell you what is p of x comma t. And once I do that, I can calculate what is x average, x squared average, any other function that I want to do. And we'll try and calculate some of these things as time goes on. Okay? All right.